All right. So what I would like to do today is finish this lecture on protein separation or this topic and characterization, and then I will start on fat characterization. Okay, for the quiz on Friday, if you want to come 5-10 minutes early, I'll try to be here early so that I can give you the quiz and you can gain a few more minutes if you need to. Okay. All right, let's get back into this. I know we talked about protein separation last time and why we do it, so I'm not going to repeat that question. Can you mention some methods of separation that can be used for protein separation and isolation? Based on size, yes. So we can separate based on size, and we talked about one important one that we use, and it is also, if you work in the pipeline, you might have encountered it. What is it? Membrane filtration. So yes, we can separate proteins based on their molecular weight, and a big industrial application is by membrane filtration, where we can get membranes of different pore sizes, and we can separate protein using these membranes. So it could be microfiltration or ultrafiltration. These two types or sizes of membranes are very commonly used in production of protein ingredients. Okay, what other than size? Yes. Ion exchange. Do you remember which company produces whey protein isolate with ion exchange? Agripur. It used to be called Davisco. It was a family owned. They were a Davis family, and they sold it, and now it's Agripur. And they had patent with ion exchange chromatography separation for whey protein isolate for the longest time. It's no longer that. But they were the only producers of whey protein isolate using ion exchange in the country. Okay, what else? Can you remember? Yeah. Affinity chromatography, and it's specifically used when we want to produce extra pure protein, like antibodies, enzymes, and specific antigens that can be used in kits. All right, very good. This is good. We can keep on. Somebody's eating something that smells really good, making me hungry. Who is it? It's not you. No. Okay. All right. So we are still talking about separation of proteins by size. We were talking about membrane filtration. Let's remind you about size exclusion chromatography. So size exclusion chromatography or size permeation chromatography or size filtration chromatography, they all mean, they just, over the years, they were named different, but all of it means the same thing. You use chromatography to separate proteins based on their size. It is commonly used in purification for characterization of the protein as a one step of purification. Sometimes when you want to purify certain proteins for understanding and characterizing, you want to use multiple ways of separation because you might have many proteins that have the same molecular weight. You might have many proteins that have the same net charge. So you might have many proteins that have similar surface hydrophobicity. So in order to purify a singular protein, you might need to separate by size exclusion, then anion exchange, then potentially reverse phase chromatography or hydrophobic interaction chromatography. So two or three stages of separation to purify. The first one usually is size exclusion. And if you remember from chromatography, I don't know where my pointer is, I didn't pick it up. What comes out first, the largest or the smallest in size exclusion? The largest comes out first because those particles that you fill your column with, which is your stationary phase, each particle have different pore sizes. So large proteins don't go into the pores. They would just migrate around the particles. If they are small, they will go through the pores and get delayed. So the smallest will be delayed and the largest won't go in and will go with the void volume. And in between, we'll have the intermediate molecular weight. Usually, we can buy columns or stationary phases that have different ranges of pore sizes. So then we can separate proteins with different range of molecular weights. So there is not one shoe that fits all, basically. All right, let's think about this question. Take a moment and think about it. I want all of you to actively think about it and provide an answer or try to provide an answer. Think. I'm sure you all will get to the correct answer. We have a full house today. That means all of you are here. Who wants 10 points? If you don't raise your hand, you're not getting it. All right. Emma, I didn't see your hand up. Okay. Everybody gets plus 10 today. All right. So if you don't like your exam grade, add 10 to it. Okay. All right. Very good. So with that said, who has an answer? Yeah. Can you explain your thought process?
Well, there are different ways that I don't think it matters by transfers, like either by charge or by weight.
Yeah.
So we all of them have size exclusion.
Yeah.
And then precipitation just allows for change charge as well.
Yep. Exactly. So I will elaborate on what Scarlett said. It doesn't matter the order. Okay. So you see here, you have two proteins that have similar molecular weight and two proteins that have similar charge. So if we start with cation exchange chromatography, I can separate protein X and Y from protein Z, correct? Because X and Y have +5 and Z has +2. So I can get Z out, but then now I will end up with two proteins that have similar charge, but different molecular weight. Then I can separate by size exclusions. I can do the opposite. So I can do size exclusion first, which is C, separate X and Z from Y, because Y has the different molecular weight, and then do a cation exchange to separate X from Z. If I do salt, I can precipitate which one first? Which one will precipitate first, or use a salt concentration that is somewhat not too concentrated? Would precipitate which one, X, Y, or Z first? Z, yeah, because it carries the least charge. So specific concentration of salt that is not very high might precipitate Z and keep the other two in solution. I can use membrane filtration of, let's say, 40 kilodalton. I can separate the 30K will be in the permeate, whereas the 90K will be retentate, will not go through the pores. So any of them, in no matter what order, should be okay. Okay, very good. All right, let's talk about SES page or page, which is polyacrylamide gel electrophoresis. That's my second favorite process or method. What was my first one? If you pay attention, huh? Kelda, thank you. So I spent a lot of time doing Kelda and electrophoresis during my master's. So at the time, page was not as easy as it is right now. So what is polyacrylamide gel electrophoresis? So you use gels that are made from acrylamide that has been polymerized so that you form a gel with different pore sizes depending on the concentration of acrylamide. So let me show you a gel nowadays. So easy for the students is you can purchase a gel with a specific acrylamide concentration or range of concentration, and it comes in a cassette. Who had done electrophoresis before? Where, Scarlett?
Genomic extraction from a virus.
For which class?
I was an internship in Newcastle University.
An internship. Okay. Who else raised hand? Yeah, where else?
I did it in high school.
In high school? You kidding? What?
Where I think we did it in Short Micro or Food Micro.
Food micro?
Yeah,
You do it in food micro?
I think so, yeah. In Short Micro maybe?
Intro to micro, maybe. I don't think food micro. Maybe.
I'm doing it in the Short Micro lab, so.
Yeah, because they teach intro micro
Yeah.
there in the same lab. Okay, so this is a cassette. And it is made up of two plates. Within these two plates, you have a gel. So all over this plate, you have a gel in the middle of these two plates. So there are different forms of polyacrylamide gel electrophoresis. There's the SDS. So SDS is a sodium diazoxide sulfite, is a reagent that you mix with your protein sample. It makes the protein all carry net negative charge. Then when you apply voltage, you have your samples loaded on the gel and you apply voltage and they all go in one direction, from negative to positive. Because they're all negatively charged, so now they're all separating based on their support size, based on size. Okay. So they're all going to separate based on molecular weight. Because now they're all having negative charge, so they're all going to move in one direction down the gel when you apply voltage, and they're going to separate based on their molecular weight size. So urea page is you mix your protein sample with urea. What happens in this case is you denature the protein, but then they will not all carry negative charge. They will separate based on charge to molecular weight ratio. So it's not as common in SCS page, but it is applied for certain types of protein. Now, if you take the advanced food chemistry new class that will be offered in the spring, you might get to see do that. We'll see. All right, and then the native page is absolutely useless, but it exists. So native meaning you take the protein, you don't add any reagent, and you try to separate it. Oh boy, it's gonna be not very good because they're not gonna separate based on anything, really. So they're gonna be all over the place because now they are gonna be separating based on charge, polymerization, and all of that, and it will be a mess. It's usually not used. Okay, so guess whose hands are these hands? Gray. No. Mine when I was a postdoc. Okay, so guess what I'm wearing in my hand? Gloves. Am I wearing gloves now? We don't do that. We wear gloves usually when you handle for two reasons. First of all, when I was a student, we didn't have these cassettes available to purchase. You had to prepare, or we had to prepare the gels using powder acrylamide. What's wrong with that story?
Powder.
Yeah, what does acrylamide do? It's carcinogen. It's a carcinogen. So we had to prepare our gels following tedious methods of preparing the gel and then pouring this gel into two glass plates that we actually glue together and put clamps. It was such a rudimentary way of preparing SDS page, but we did that and used to take the entire day to prepare a gel and pour it and then load the sample. And then the next day, your advisor comes, looks at the gel and tells you, no, redo. Isn't that? So I don't do that to you, Andressa, because usually the gels are poured well for you and you don't have to worry about being poured wrong. Okay, so they come in and you have like what we call this a comb. So when you take that comb out, then you'll have wells. And when you prepare your sample, you can load them using very, very thin pipette tips that the tip can go into each well, and then you can pour your sample, about 5 microliter to 30 microliter sample. So, but you don't take the comb out before you position your cassette in this container. So usually you can run 2 cassettes at the same time, and then you fill with what we call running buffer. And then once your compartment is filled with buffer, then you can ease out the comb so that your wells don't collapse on each other. Then you can load your samples and connect this to a voltage unit. So where you can run voltage and all the proteins will move in one direction from negative to positive. All right, after you're done, then you take out the gel. Okay, now I can take out this comb. I'm not loading. Of course, you never run your gel without pulling this off. Otherwise, your buffer will not run properly and your protein will not separate. And look, this is very handy. So you have a unique, a very cool spot on this cover. Then you can put your cassette here. Did you know that, Andressa? And then you break it open. And then gently, this is an expired gel. Hopefully it doesn't break. And gently you open it. You see the breath? Oh, that's it. Can you touch it? Oh no. Do you can you touch acrylamide? Oh. Why? How? It's carcinogen. But I'm touching it. What's wrong with me? What's wrong with me? I don't care. No, when it's gelatinized or gel like that, it's not fun. So you can touch it. Oh, why do we even make one? No, it's not so really cool. Not really. So it seems like people like to touch it. Oh, it's just like a window clip. It's just like how face it out. It's called. Anyway, so we take it out and then we stain. So at this step here, I put the gel and I'm staining it with Comasi blue. So the protein will react with Comasi blue and nothing else will react. So if you have sugars, fat, whatever you have, they won't react with your Comasi blue. So you do the staining and then you wash with either reagents to help. We used to wash with acetic acid reagent, but now just washing with water is fine. And you just leave it washing with, you change the water multiple times, and then you end up with a gel that is clear background and only the proteins are stained. So pretty cool. So these, we usually run a marker with different molecular weight proteins, and then we can identify our proteins based on their molecular weight. So in this case, we ran standards of a type of protein in soy and another type of protein in soy. And then we ran our soy protein isolate and a couple of samples that we hydrolyzed targeting specific components. And then we looked to see what the enzyme hydrolyzed. Did it hydrolyze this component or the other component? So that's one application for STS page. But I want you to remember that with electrophoresis, we don't usually use it as preparative, meaning we do not collect protein. We separate them so that we can look at them, identify them, determine differences among the samples, but it is not a step we use to isolate protein, take it out, and use it for something else. So this is important to remember. So when depending on the question I would ask you potentially in the final, SDS page might not be a correct answer if I ask you to purify a protein. Okay. This will separate the protein for characterization rather than just collection. Okay. Questions? Right. So there is separation by isoelectric focusing. Meaning here, we're separating the protein not necessarily on their molecular weight basis, but on their isoelectric point. So this is very much used as part of a two-dimensional separation by electrophoresis. So what happens here is you generate a gradient on a piece of acrylamide gel. So the gradient is a pH gradient. So you load amphalites, which are compounds with different charges. They carry different charges. And then you run a voltage, and then you will have a gradient of different pH range across that entire acrylamide gel. After you create that gradient, you load your protein sample and then also apply the voltage, and then the protein will migrate and will stop migrating when it gets to its isoelectric point or the pH at which it has zero charge. Then it will press P. And then you separate the protein. But like I said, this is often used as a two-dimensional electrophoresis, where we do the first separation based on isoelectric point, and then we get another cassette, like this one, but the cassette has only one well. From beginning to end, you only have one well. So in that well, you slip in that piece of gel that separated the protein based on isoelectric point. Then you run your electrophoresis on a gel to separate by molecular weight. By STS page, you separate by molecular weight. Then you get proteins separated on two dimensions, isoelectric point and size. So if you look at the blue band, if you think it's one protein, it's separated into two proteins of different molecular weight. If you look at the yellow and the orange, they had the same molecular weight, but separated based on their isoelectric point. So if you run one or the other, these proteins would not have been separated. Usually this is a technique done in Western blot, where you do two-dimensional separation, and then you incubate with antibodies to determine presence of allergens or other antigens. Okay. So very common for that particular application. Have you heard of capillary electrophoresis? No, nobody has encountered it in any job? No. Okay. So the capillary electrophoresis is similar to an HPLC unit, but instead of having a column, like a regular HPLC column, you have a capillary column that contains material similar to you know, it could contain acrylamide gel. So that would be similar to separation by electrophoresis, but in a format of an HPLC. So you would have a column here, you separate the protein and you run a voltage. So let's say you have STS page in there, they would separate based on size. They're all negatively charged or positively charged. Well, in STS, they're negatively charged. So they will be moving from negative to positive. And then if you have a silanol groups in the capillary group, so the capillary tube, so they will interact via ionic interaction. So that would be negatively charged, the capillary tube, and your samples will be interacting, positively charged, interacting with the silanol and separating. And then you would have a detector similar to HPLC. So basically you separate the protein, but instead of a regular running buffer, you would have a buffer between two electrodes and a voltage, and then a detector similar to HPLC. So now moving into protein characterization, one of the most important characteristic of the protein is its nutritional quality. So if you remember from earlier on in the semester, we talked about the nutrition label and we said daily value of protein is not mandatory on the label unless you are what? Making a claim. A good source of protein, a high source. Huh? Oh, for little babies, yeah. For babies that need proteins to grow. So yes, but it's an important characteristic, especially now with the craze of the protein and everything should be high in protein and for their nutritional contribution. So we need to calculate that nutritional quality aspect. The first thing we need to determine is amino acid composition so that we can identify the presence and content of essential amino acids. The next thing that is important is digestibility. Processing can impact protein digestibility, for example, or plant proteins are harder to digest than animal protein. So it's a big component of nutrition quality. We can't digest this protein, no matter how much good amino acids it has, we cannot absorb it. So digestibility is important. Anti-nutritionals are important, like trypsin inhibitor, presence of lectins. These are proteins in beans, especially raw beans. If we eat a lot of raw beans, then we could potentially have some inflammation symptoms due to lectin. Phytates, they would bind with the protein, make them less digestible, same as saponins and tannins. They would bind with the proteins, precipitate them, make them hard to digest. Okay. How do we determine amino acid composition? We break down the protein into their building blocks. So we take the protein, we hydrolyze it completely into amino acids. So we do acid. I just updated this to clarify that we do acid hydrolysis, but we also have to do base hydrolysis. So you prepare your samples in two ways. One, you digest with acid, but acid degrades tryptophan, and tryptophan is an essential amino acid. Then you take another sample and you hydrolyze with base so that you can get the tryptophan content. All right, so we break the protein by hydrolysis with heat, for a specific amount of time, and then we take this digest that has now individual amino acid and we run it through HPLC, anion exchange, or reverse phase. Usually more common is reverse phase, but not all amino acid absorb blood. Do you remember what amino acid absorb blood? Remember at all? What? What? You want to say something?
No, I just remember the day and I remember you saying like three because I just started listing amino acids. I was sitting over there. Yeah.
Well, not all hydrophobic. Some are tyrosine. Huh? Tyrosine is one. I mean, histidine has a cyclic in it. It's a good try. Huh? What? No.
Aspartame.
No, aspartame.
Oh, no, aspartame. Aspartame.
Aspartame. No. Okay, let me take you out of your misery. So there's some tryptophan. What's that? Yeah, okay, thank you. Tryptophan, phenylalanine, and tyrosine. They are the only three that actually absorb light. So what do we do? If we want to use UV or fluorescence, we have to derivatize them with a compound that will give us either a fluorescence or a chromophore that absorb light. Then we can measure using UV detection or a visible light detector to measure absorption or fluorescence. Then we quantitate all of these wonderful amino acids. Then we can determine something called PDCAS, which stands for Protein Digestibility Corrected Amino Acid Score. It's a mouthful. You've heard of it, right? This is what we use. It's the official method that we use to determine percent daily values for the nutrition data. So it requires that we measure digestibility, and then we get the amino acid score, which is the milligrams of the first limiting amino acid. Let's say in cereal, the first limiting amino acid is in wheat. What's the first limiting amino acid? No, Emma, you know this. I'm sure you know this. If I say lysine, would it ring a bell? No, it won't ring the bell for any of you. Lysine is the first limiting amino acid in cereal grains, which is really a problem for gluten protein, for example. Corn proteins almost have zero PDCAS because of how low lysine is in corn. Anyway, so you get the milligram of the first limiting amino acid in your test protein and divide it or relative to the same amino acid in a reference protein. And usually your reference protein is KC. So you get a score from 0 to 1. And then you do the digestibility, which you get a score from 0 to 1. And that's why your PDCAS is between 0 to 1. So we can do digestibility testing using the official method that is used for label is animal-based, which is getting a lot of, some companies don't want to use animal experimentation. So trying to get other types of methods that do not sacrifice the animals. But as of now, this is the official method. So what you do is you have rats that you would feed them your protein and you feed them your reference protein or another group for reference protein. Then you measure nitrogen in the stools. So you know the nitrogen intake, and then you measure nitrogen on the stool. You know how much nitrogen is absorbed. You calculate percent digestibility or in a score of 0 to 1. Then you use that score, digestibility times amino acid, to get that PDCAS, and then you use the PDCAS to determine percent daily value. So if you have 10 grams in your serving, and you have a PDCAS of 0.8, you really have 8 grams available protein. So, and then you take the 80 grams divided by the 50 grams per day that you need, and then you calculate percent daily value. That's how you do it. Okay. Protein efficiency ratio, which is PER, it is the official method in Canada, not the official method here. It is only relevant here in the US to babies, because how it is used, that you use baby rats and you feed them protein and you measure their gain weight over a specific period of time. And that is, baby rat gain weight is comparable to human babies gain weight. Yeah, we're very, very similar to rats, apparently. So we don't use it for older kids and adults because you would hope that you don't gain weight with every time you eat protein, right? So gaining weight is not related to how much protein intake. So that's why PER is not an official method for use in children and adults. But the way it is that you get the total weight gain for test group and the total protein consumed. That gives you the protein efficiency ratio. You correct it by a reference, usually casein, and then you get it out of 1, score of 1. All right, so other tests for nutritional quality is all the essential amino acid index. So we get the index for all of the essential amino acids, which are 9 essential amino acids. We can determine in vitro digestibility. We do that in the lab a lot, so that we work with companies that they don't really want to do in vivo. They don't want to use animals. So we get really Megazyme kit that has been developed to give us a calculated PDCAS. So you just use enzymes, digestive enzymes, and predict the digestibility as it would be in vivo. Lysine availability, this is important to determine the effect of processing because lysine reacts with what? Reducing sugar in a Maillard reaction would be one of the first amino acids to be lost during processing. So it is monitored that way. Then there is a whole list of protein structural characterization. We do that a lot in my lab to look at structural characteristics of the protein, whether it's molecular weight distribution or changes in molecular structure, like surface charge, how much the protein carries on its surface. It will impact how it will interact with water. Also, surface hydrophobicity. The more hydrophobic the protein, the less it's going to interact with water. And then protein denaturation. All of these characteristics are important for their functional behavior in food systems. This is a big deal now, as proteins, like I said, is being dumped into a lot of different products, but they have to live up to their potential by being functional. They emulsify, they gel, they can be solubilized, they can be texturized into meat products. So these are functional properties that we test. If you want to know more, they're all in this one big chapter in your book. Light bedtime reading. Very light. Okay. All right. I have 5 minutes. And guess what I'm going to do with these 5 minutes? Huh? You want me to be done?
No, I'm sorry.
Well, let's just chat, okay? We'll get us started, but I will repeat everything on Friday. But let's just spend a few minutes chatting. Okay. Who in this department like fat characterization? There you go. All right. Who likes carbohydrate characterization? No? You? Okay, great. Why isn't it moving? Yeah, okay. What do we know? Who works in Fernando's lab?
I work with flavor.
Okay, I'm not looking at. But we're here to learn. I don't expect you to know this, but probably you came across peroxides in food chemistry. Okay. From what you remember, are they primary or secondary oxidation products? They are primary oxidation products. So, is A correct in that case? No, they do not indicate advanced stages of liquid oxidation. Secondary metabolites and the presence of secondary metabolites of oxidation will indicate advanced stages of oxidation, like hexanol. Hexanol is a secondary lipid oxidation product. Iodine value, have you heard of that? Okay, you haven't. We're going to talk about it, but C is correct. Using the iodine value, which it determines the extent of polyunsaturation. The higher the number of unsaturated double bonds, the higher is your iodine value. So if we oxidize lipid, what happens to the double bond? Do they increase or decrease? So the oxidation usually attacks double bond. And then the double bond becomes no longer double bonds, right? So measuring iodine value, it will change, it will decrease in an oxidized oil because your number of double bonds will be lower. And then we're going to talk about that in more detail. But for now, just put B and C is correct. For this one, saponification value has nothing to do with fat saturation. This would be iodine value. So false, and next time we're going to talk about all of these wonderful terms that are so important for the fat component of the food. All right. I'll see you on Friday. Oh yeah, today is Wednesday. If you have the fiber extra credit, please give it to Andresa. If you forgot, bring it Friday.
Okay.
5 points. Why not?
The quiz.
Huh?
I have a question about the quiz.
Yes.
So it's just up to carbs, right?
Oh yeah, the quiz, since I have you all here, it will be only till the last lecture on carbohydrates. So no proteins or fats. All right.
To meet with carbs.
Proximate analysis. So it will be moisture, ash, fat, protein, and carbohydrate.
Thank you.
Yeah, do you have sauce stay hungry for office hours that were busy during that time? Are you available?
Today?
Yeah.
Today I got someone, but you can come if you come at 4, I'll meet with you first before it's just an intern.
Oh, okay.
And they all know that this is my office hour. If a student comes,
Okay.
okay.
I'll come back.
Oh, yeah. Okay, and if you fit in a little later. No, we get trial.
Okay.
Okay.
I think you got.
Andresa, can I give you this? This?
The median.
Oh, I'll carry it. I'll bring it to the lab.
It's the part for the camera, I'll bring it to the.
What is that?
It's like a heater, the thing heater.
For who?
Because the back. Yes.
Oh.
So I'm.
Fiber? It's on the carbohydrate slide. The very end.
But she sent a video.
This table is calculated. Like, just follow. It's just like.
Oh, it is. Awesome, so we don't have to pay Jordan. Okay.
Still like check what your emails are, you know, a lot.
Yeah.
Thanks. Everyone's so I made an active choice today. So I was like, you know what, today it was so 50-50. When I woke up, it could either be a really good day or a really bad day, and nothing in between. And so I did on my whole outfit, and then I was deciding to do my shoes. And I was like, well, if I put on these shoes, it's gonna have to be a good thing. Because that's just how it feels, you know? So I was like, you know, I think I can quit, and it's been great so far.
Yeah.
Thank you guys. I know, yeah, it's the shoes, like, it really is. Yeah, you know, Adidas, they have a really, really cute pair of things, but I had just gotten a pair of Pumas, and I was like, I don't wanna buy Adidas things anyways, that's why I got the Pumas. But they have their Adidas Taekwondo shoes in silver. So cute. So,
I just have really big feet, so I kind of stay away from kids. Oh, no.
Right. Stuff.
seems valid, or I think you can embrace it, you know? Just embrace it. It's kind of fun.
And just want to.
No one's gonna say that. They might think it, but they're not gonna say it. That's, yeah. And that's okay.
Awesome.
I will.
But it's out of love.
No, it's because she told my dad.
She do it before. Well, big feet means that you have big nails, so it's really a compliment.
I only wear a size of my bag.
Two other.
That's pretty average.
Yeah, that's a great thing.
I have small feet.
I think my feet have been shrinking, because I used to be a 9, and now I'm like slowly getting to my feet.
Same.
You know?
I have small feet for my height. I'm 5'10".
See, I'm 5'6", so it's pretty regular. That is pretty regular.
Yeah.
These might be a size 10, but sometimes I buy like a thing.
Yeah, no, it was just made me feel like
Oh,
We can sit together.
Your size.
Like, we can video calling with it. Oh, you're aware?
There's so much dog hair in
I don't know what we're going to get at.
Yeah. Just like.
You can see like golden shoes, they have mostly neutrals, but then they have also size.
Yeah, oh, yeah,
And that, yeah, they're so fun.
All right.
They really are making me want a pair of shoes like that. And I just don't need it right now. I've been putting literally all of my money on shoes right now. It's really bad.
It's okay, girl, I'm not.
It does